What we're going to look at now is a shortcut to differentiation, one of many shortcuts. It's called the power rule, and it deals with finding the derivative of a function like this, where alpha up here is just some real number. This is x to the alpha. And what the power rule tells us is that the derivative, f prime of x, is equal to alpha x to the alpha minus 1. It's a shortcut. Now, I want to show this is true as long as alpha is a positive integer, and then I'm going to show it's true if it's a negative integer. So, before I do that, before I show that this formula works, I need to think about how would we find the derivative using the difference quotient. Well, remember what we would do is we would say f prime of x is equal to the limit as h goes to 0 of x plus h to the alpha minus x to the alpha over h. This is the way we would do it. And then we would expand out this x plus h to the alpha and simplify. So I need to take a minute and talk about a way to expand out this x plus h to the alpha. Now, perhaps you've used Pascal's triangle to do this. Well, I want to show you, remind you about the binomial expansion theorem. And before I do that, I need to talk about this thing called combinations. A combination, okay? A combination is something that it looks like this. We could say 5 and then maybe have a 3 down here, okay? Or sometimes it's written this way, 5C3, like that. But this is a formula involving factorials, and it goes like this. This is read 5 things taken 3 at a time. And the formula goes like this. It's 5 factorial over 5 minus 3 factorial, 3 factorial, like that. That's a combination. And then we would just simplify this out. But my focus here is not to talk about how we simplify these factorials. My focus is just to show you how we could use the binomial expansion theorem to expand this x plus h to the alpha. And it involves combinations. Now, in general, we could say this. If we have n things taken r at a time, okay, n things taken r at a time, that formula looks like this. N factorial over n minus r factorial. That's what that is. That's the formula for that. Now, the binomial expansion theorem, let me show you how this works. Let's suppose we have x plus h to the 4th, for example. Well, the way we can expand this is we go like this. We go 4 things taken 0 at a time, x to the 4th. See, in other words, these combinations generate the coefficients. We normally use, perhaps you use the Pascal's triangle to generate these coefficients. Well, the combinations do the same thing. So this right here will give you 1, and then we say, okay, now we have 4 things taken 1 at a time, and this is going to be x cubed h, see, like that. And then we say, okay, this is going to be 4 things taken 2 at a time, x squared h squared. And we keep going. And then you can see with the next, it goes 0, 1, 2. This is going to be 4 things taken 3 at a time, x h cubed. And then finally, 4 things taken 4 at a time, x to the 0 now. Okay, so this is just h to the 4th. This is one of the ways we can expand out a binomial. And these combinations generate the coefficients. See, look at this first one. 4 things taken 0 at a time. That's 4 factorial over 4 minus 0 factorial. See, just using the formula times 0 factorial. Well, remember 0 factorial is 1. So really, all we have here is 4 factorial over 4 factorial, which is 1. And we know the coefficient here would be 1. Let's look at this one right here. This is 4 factorial over 4 minus 1 factorial times 1 factorial. Well, let's see what that is. That's 4 factorial over 3 factorial. See? 4 minus 1 is 3 factorial. And we could write that as 4 times 3 factorial over 3 factorial, right? And that's just 4. So notice this first term here is 4. Now that's something I want to focus on, because notice, well, this second term in a binomial expansion is always going to be n factorial. It's always going to be n things taken one at a time, like that, right? This is 4 taken 0, 4 taken 1. If we were just expanding x plus h to the n, then this would be n things taken one at a time instead of 4 things taken one at a time. And look how that looks. This is n factorial over n minus 1 factorial times 1 factorial. Well, that would be n times n minus 1 factorial. I could always, just break this down this way. And then I have n minus 1 factorial, which this is just n. My point here is not to get too much involved in how we simplify these factorials, but just to show you this term right here, n, the second coefficient, the first coefficient is going to be 1, the second coefficient is going to be n. See here, the second coefficient was 4. So notice, x plus h to the 4th, the second coefficient was 4. If this was x plus h to the 5th, this coefficient would be 5, and so forth. So, that being the case, let's think about this derivative, the limit as h goes to 0 of x plus h to the n, or alpha, I think we were saying, alpha, x plus h to the alpha minus x to the alpha over h. Now, if I expand this out, this first thing right here, look what I'm going to get. I got to remember to carry my limit along. Look what I'm going to get. I'm going to get x to the alpha plus, the next term is going to be alpha and a 1 right there, x to the alpha minus 1 h, right? That would be the second term. Look, match it up with what I've got up here when I had a 4 instead of an alpha. See that? Okay. Now, we could keep going all the way to the end where I've got alpha over alpha things taken alpha at a time, h to the alpha. Okay. This right here is the expansion of this. Minus x to the alpha all over h. Now notice this x to the alpha and this negative x to the alpha cancel. And look at what happens here. Every one of these terms have an h in them. This first term has an h to the first power. Everything else has an h to a higher power. So here's what we can do. We can factor out that h. Okay, we factor out the h, and then we have this. Here we have, this remember is alpha, x to the alpha minus 1, and then plus all the way out here to h to the alpha minus 1. See, I just factored out an h from all of these. And these h's cancel. Now, I'm ready now to evaluate the limit, but notice the only part of this that doesn't have an h in it, in other words, the only term up here that's not going to go to 0 is this first term. So this limit is alpha x to the alpha minus 1. Now that shows that this. If we have f of x equals x to the alpha, where alpha is an element of the positive integers. If that happens, then we've shown that f prime of x is equal to alpha x to the alpha minus 1. So, for example, let's suppose that we have f of x equals x to the 7th. Then we know that f prime of x is equal to 7x to the 6th. See? We just subtract 1 from the top. So this shows the power rule is true provided that alpha is a positive integer. Now let's suppose we want to look and see, well, what happens when alpha is a negative integer? So let's suppose that we have this situation here, or let's just suppose that we have a situation like this where we have x to the negative alpha. And I'm going to say, I'm not going to call alpha a negative integer. I'm just going to say alpha is a positive integer, but you've got a negative in front. Well, that means that you have, this thing is 1 over x to the alpha, right? So what we've got to do is we've got to figure out what the derivative of this is. Okay, so I'm showing what happens if you have x raised to a negative integer power like this. Well, let's see what happens here. The derivative is going to be the limit of 1 over x plus h to the alpha minus 1 over x to the alpha over h. Right? Now remember how we deal with simplifying the difference quotient in this situation. We multiply by the denominator, the common denominator. So look how this would look. This would be the limit as h goes to 0, and I have 1 over x plus h to the alpha, and I'm multiplying by x to the alpha, x plus h to the alpha. See? That's what I'm doing. Now I do that every place. So I've got 1 over x to the alpha. I multiply it by x to the alpha, x plus h to the alpha. And down here, I've got h times x to the alpha, x plus h to the alpha. Okay? So I just multiplied everything by that common denominator because I wanted to clear out those denominators. Now look what happens. These cancel, and let's see what I'm left with. What I'm left with is the limit as h goes to 0, and let's see what happens here. I've got x to the alpha, see right there, minus x plus h to the alpha over h, x to the alpha, x plus h to the alpha. Now, if we expand this out right here, notice what we're going to get. We're going to get the limit as h goes to 0, and I get this. I get x to the alpha minus, okay, here we go. I've got, first of all, this is going to be x to the alpha, okay, minus, remember what the next term in this expansion is. It's alpha x to the alpha minus 1, h, and then we come all the way down here to the very end where we've got h to the alpha. Okay, and then we've got h, x to the alpha, x plus h to the alpha. Okay, we're almost done here. Okay, now look, these cancel, and notice everything's got an h in it, but this only has a single power of h. So when I factor out and divide out the h's, here's what I get. I get the limit as h goes to 0, and look what's left up here. I've got negative alpha x to the alpha minus 1 minus dot 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 all the way out here to h to the alpha minus 1 because I factored it out and divided it. And now down here I have x to the alpha, x plus h to the alpha. Now I can evaluate this limit. So I just let h go to 0, and here is my derivative, negative alpha, x to the alpha minus 1, all over x to the alpha, x to the alpha. In other words, what I get is negative alpha, x to the alpha minus 1, over x to the 2 alpha. Now let's see what that is. If we simplify it a little bit, we've got negative alpha, x to the alpha minus 1. And remember, if you have the same base, you can subtract the exponent. So minus 2 alpha. And that will give me negative alpha, x to the negative alpha minus 1. Yeah, there it is. Now, let's think about that. I'm saying this verifies the power rule. Remember, the power rule goes like this, that if you have f of x equals x to the alpha, then f prime of x is equal to alpha x to the alpha minus 1. And I'm saying that will work even if this were negative alpha up there. So let's see how this would work. So let's suppose I have f of x is equal to x to the negative alpha. And let me apply this rule. Well, I bring the negative alpha out front. And then I subtract 1 from what was already up here. Yeah, there it goes. So you see, it matches up, right? I just brought this down front and then subtracted 1 from it. So look at this. The power rule works for negative exponents too. So let's look at this. Let's suppose I've got f of x is equal to x to the negative 7. Well, the derivative, well, not inverse. What am I doing? Let me fix that. Okay. F prime of x would be negative 7x to the negative 7 minus 1. Now, you have to be careful. The tendency might be to add this and call this a negative 6. But no, this is a negative 8, right? See? Negative 7 minus 1. So there's my derivative right there. So this is the power rule for even if you have x raised to some negative integer power. Now, look, this thing also works for rational numbers. Now, I'm not gonna show you yet. I'm not going to verify that for you yet. Let's just take that as a given, that if you have something like this, let's suppose that you have x to the 2/3 power. What I'm saying is the derivative is going to be 2/3 x to the 2/3 minus 1. See? So, in other words, we have f prime of x is equal to 2/3 x to the 2/3, and I like to just say minus 3/3, get a common denominator in there. So we've got 2/3 x to the negative 1/3. Yeah. So what I'm saying is this power rule right here, x to the alpha, works for alpha being a real number. So where alpha is just an element of the real numbers. It doesn't have to be an integer. It could be a rational number. It could be an irrational number. And all we've done is explored what happens if you have positive and negative integers. But as we go along, we'll look at the other options.